So yes, yeah, there was apparently some difficulty with the mic, so I'll just restart here. Today we have week 7 of machine learning course, and the topic is basically very similar to what you have been going through in the computer vision course from different architectures of like computer vision models, tasks, but in particular CNNs. So this particular lecture decided it's about time that you guys are actually familiar with the topic quite well. And it's not going to be that much more difficult for you to get the information, to comprehend the information for me if I ever switch to English. So yeah, let us get started. This particular lecture today is basically more of a general overview of different like tasks in computer vision, in particular the CNN architecture, as well as it's more focused on kind of a useful aspect, which is how you train neural networks correctly, deep learning models correctly, regularization, early stopping, dropouts, all different techniques, how to apply them. And I think I'll try to go in depth with them and explain as much as possible. So yeah, let's get started. This is a quick reminder of how like a neural network architecture in a typical space looks like. So basically, we have obviously affine transformations, which is basically matrix multiplications within the layers. We have different kinds of layers for like the whole network architecture. There's an input layer with input data, obviously. There's an output layer where we just get the processed like weights and information from the network and try to classify something, perhaps if it's a classification model. And there's a hidden part with multiple hidden layers. If there's more than 3, I think, according to topology, the network can be called a deep neural network, so 3 or more. And obviously, every single connection is just a matrix multiplication with existing like initialized weights with a certain bias term and the actual input. So, and of course, there's an activation function inside as well, inside of every part, every single connection. So the activation function basically serves as a nonlinearity, most times than not, just to approximate different decision boundaries or like to better extract features nonlinearly. So basically, it can be anything, it can be like hyperbolic tangent, can be sigmoid, can be rectified linear unit, ELU, GLU, and many others. So yeah, as you may well know, the CNNs or convolutional neural networks are just a special subtype of an NN which pre-process data in a grid-like topology. A grid-like topology, simply put, is basically all those kernels that you've seen so far in CNN, where you just apply like a 3x3 filter, extract information, and create feature maps. Basically then downsample the image by applying max pool layer, for example, or average pool. This is what a typical grid-like topology looks like. So yeah, the grid-like topology models do not necessarily limit themselves with computer vision applications. Also such things as time series data. For example, we have like tabular 1D data on time intervals is also like has a very similar pattern. And basically for 2D, we have a 2D grid of pixels. This can be applied for 3D as well, where we have a third dimension, like depth, for example. This can be applied for 4D dimension, where we have a time component as well, for example, in videos. And yeah, basically that's that. So convolution, as you also well know, is just a very standard procedure in CNNs. Basically revolves around applying a kernel of a fixed size of an odd number, for example, 3x3, 5x5, 7x7, and performing matrix multiplication within the existing piece of an image, so like 3x3, just laying the kernel on top of this of certain piece, applying the transformation, basically an affine transformation in a way as well, and then just getting the respective output, which is usually a subsampled feature map, so which is lower dimension, depending on like what stride you're using. Remember the concepts of stride or padding, whether you want to pad zeros, like the edge of the image with zeros to prevent the image resolution to get lost, to get reduced rather. or stride is just the window how much you want to step right in order to apply the next kernel convolution. Yeah, but basically, simply put, this is all just a matrix multiplication in many layers, usually for CNN. Yeah, so this is what it looks like. Basically, there's an image of Mario. It is not a standard square image. It has like, I don't know what it is, but it's most likely 9 by 16 or something, maybe a bit less than that. And I mean that just a size ratio. And basically, we have a kernel 3 by 3. We just overlap it with every single piece, every single pixel, for example. If we have like stride 1, so we just roll from left to right on every single pixel. We have like stride 2, we just skip 1 pixel and then go on to the next one. So every second pixel just gets convoluted. And then basically the output image is going to look like something in the right. For example, in this particular case, I suppose the outer boundary, so the edge of the image is padded with zeros. That's why we can basically also like perform the convolution on top of the image where there's actually no pixels, but we just we imagine them, we basically input them there, insert them there, and this lets us preserve the output resolution size. And the further it goes, the more we go into the depth of the CNN, the more specific features can the model extract. So this is a process of automatic feature extraction. There's no handcrafting whatsoever involved. There's just an automated version of like all those old classic traditional computer vision things like edges and I don't know, lines and diagonals and segments, perhaps some key points. It's all kind of in there in the process of convolution. So the very first layers in the deep CNN, they extract the general pattern. Like for example, that this is perhaps some kind of person or like a game character or whatever. Just does not know specifically anything besides that. So if just after first few passes, first few layers, I mean. Then in the middle layers, the model extracts more specific information. Perhaps this looks like a guy who's rather short, who has like a certain cloth piece on him, has probably a hat, probably has a mustache or something. And then, but yeah, no details yet. In the end, the very last convolutional layers with max pooling and everything, yeah, very last CNN layers, they basically extract the most precise information, the most particular points of interest that distinguish this particular image from all the others. So they see that button, or not the button, that like fixer or clipper on Mario's like pants, the white one. They also like recognize this probably like some cartoon character or like video game character, and like know the color of like red and blue, very typical shape or very typical pattern or combination rather. And yeah, basically giving the most details about the picture, about the image that's processed. It's just basically the analogy that I gave before in one of the computer vision lectures is when we have top to bottom like precision extraction. So first, as a human beings ourselves, we just our vision system with the retina on the eyes is first when you just enter a very like unknown venue. For example, you enter like a library inside the Hill Academy. You first mention like or first basically notice the general patterns like the walls, the doors, perhaps the stairs, maybe some person, potentially some further away shape of a person who's like climbing down the stairs and probably trying to exit the library as well, but nothing else besides that. And then like a couple of seconds pass, your eyes adapt, your like whole organism and your whole body adapts, and you start to notice more like specific patterns. You like notice there's a book return like cupboard in the left, or like where you can actually throw back books which you borrowed in order to not wait and not to turn them back in. Or you notice like a clock on the wall, you notice a couple of like plants that need to be like watered or something. because there's a lady coming towards them with a bottle of water. And then in the end, a couple more seconds pass, or maybe even moments pass, not necessarily seconds. You notice very specific and very like tiny pieces of information that you will never actually see without actual focus, which is like a text, tiny text written on this cupboard with book return, like what it says, please return, blah, 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 have a good day, la di da, or something along those lines. So our human like vision cortex, vision system works in very similar, right? As like CNNs do. So it's a very easy analogy to make in order to understand things better here. Yeah, the CNN. There's just a rather old architecture called CafeNet. There was once a deep learning framework besides TensorFlow, besides PyTorch. There was a framework called MXNet, and there was a network called Cafe. So basically, I think this particular architecture references that particular like those developers and researchers who came up with a model back then, and they had like this framework, which I think it was not necessarily in Python. This was like C++ or C# or God forbid Java or something. I don't think it was Java, but it could have been C#. So yeah, but Cafe and MXNet, they outlived themselves. They became completely obsolete with PyTorch, with TensorFlow, with JAX now even. So the architecture looks like this. There's just a very standard like image that you are familiar with, where we have an input with 3 channels like RGB, right? And then there's like dimensions of the image are 2 to 7 by 2 to 7, and we apply different kernels to them. For example, a kernel of 11 by 11, right? And we extract some feature maps. So the image is downsampled after that. So perhaps 11 by 11 like removes 5 extra pixels, plus we go down a bit. Maybe there's some extra operation. Yeah, but in the end, like there's first PL, first pooling, I think that's what it stands for. We have like a different dimension already, much reduced, 55 by 55. And we have 96 depth, so 96 feature maps that were created on the first convolutional step. So like there's a pooling layer that we just pull everything, downsize everything, and then we get an image 27 by 27. So reduce it by the factor of 2. So 55 times 2 grounded is 27. And then there's another filter applied, for example, 5 by 5. And we get another like stack of feature maps. Now we have like 256 maps. Then there's another pooling layer. And basically the original image reduces more and more. And we get, in the end, just 384 and of 13 by 13 and like 256 in the end feature maps of 6 by 6. And then this is kind of this main part that I usually show is a feature extraction part where only operations of convolution pooling are permitted, so to say, or are figurating, getting engaged. Whereas there's the other part very important in every single CNN is the fully connected part, like fully connected part where we do the actual classification, for example. So there's always a flattening layer involved. So when we flatten things out over here, so I'm not sure, I think 2 to the power of 8. I don't know if that's 36, but yeah, something like 4096 neurons in the end. There's usually this standard linear mapping in the old models where there's just maps in itself with some kind of activation, very standard, like nothing fancy. And in the end, this output just gets processed further. The weights, the logits, the weight from the actual neurons are being processed via softmax, and we get like 1,000 classes, for example, for ImageNet, and then these like 1,000 classes, they just get summed up. Their probabilities get summed up to 1, and then we just choose either top 1 or top 5 according to ImageNet's like standard metric definition. Yeah, so nothing too new for you actually. Yeah, convolution and pooling operations. Yeah, basically there are of course 3 channels. I think This is less in depth that we went through like on the computer vision class for this topic. But yeah, we have basically not one channel in each image. We have usually like colored images with 3 channels, RGB, not just gray. And the thing is, there's nothing too complicated. We just apply the filter to every single channel, and then we sum them up with bias. So there's K1, K2, and K3, which are the outputs, respective outputs of applying. K1 is for red, K2 is for green, and K3 is for blue. And then we just add bias, and we get the output, the feature map, like not the feature map, but the kind of the combined output for the future feature map, as you can see in the right. And that once we got everything settled, once we convolved our image, we just apply usually in order to ease up, to make the computation easier, ease up the computation, and make the model require less resources. We just reduce the size of the image by applying pooling layers. This can be an average pooling layer, it could be max pooling layer, basically, usually 2 by 2. And it just takes out either an average of like 4 pixels or the maximum value of 4 pixels, dropping out the rest. Effectively reducing the dimension as well. Yeah. So for upsides of CNNs, basically there's such concept in CNNs as weight sharing. It basically there's everything interconnected inside the architecture in terms of convolutional part, feature extraction part. And basically, it's kind of a built-in regularizer, which acts as a kind of something that effectively prevents overfitting, makes the network not like too susceptible to changes in the new data that it has never seen. And this is good. CNNs also kind of dive deep in the structure of data. They kind of recognize different patterns, invariant features, so they can actually extract very useful information, and they can be considered very efficient for certain tasks. Like, for example, a very good example here is like one of my colleagues right now, the junior colleague from my work, was doing like stable diffusion for stable diffusion generation for like car designs, like the paint, not the paint, but like the decals, and everything this has to do with like fine-tuning the car's look with like this different patterns. So the client came with us with like 2,000 to 3,000 different designs of these kind of decals. And in the end, they asked us to kind of cluster them in different similar categories or like groups. And this had to be done before being able to generate like something similar from one of those kind of clusters. One has to create clusters, and in order to create these clusters, basically the feature extraction has to take place. And what my colleague used was he used CNN. He used EfficientNet, I think, or maybe even JCVAT, like Vision Transformer. So and the model pretty efficiently extracted different like kind of half warps, full warps, like different styles and colors and patterns. So yeah, this is what exactly the case where using CNNs is much better than even referring to a human expert, because this is going to take so much time for a person to manually, by hand or like by eye, differentiate between different classes and different designs. So CNNs excel here. Yeah, also transfer learning, you all know that. You can just download the model right now from Torch Vision ResNet from Model Zoo, like TensorFlow Model Zoo ResNet 18. It is pre-trained, comes with weights from ImageNet. And then you can practically use any classification task with images, like with the multiple classes. This could be something very different from ImageNet entirely, but it's going to boost the performance of your model significantly. So a kind of, this is a prior information, prior knowledge the model has. And yeah, with this prior knowledge, it can just grow on to be better in a new task it has never done. Image translation, yeah, models usually robust to that, the CNNs. The same goes for parallelization and ease of implementation. Not particularly hard architecture to kind of parallelize. If we want to compute more feature maps, do some of the things that might require multiple GPUs. That's not hard to be done. And yeah, variable input size. So basically regulating everything we want in terms of like convolutional kernels. Something else besides that, that's all tweakable, and that's good. But that's only for FC, not for FC part, but for the convolutional part. As for disadvantages, of course, I usually like talking about those pertaining to my area of expertise. The CNNs, there's like a lot of problems that have to be coped with before making them efficient models in production, even, or like in research some way. So there's of course a problem of data. The more data, the better. It's not likely that the model is going to work well on 100 images. That's why we need more, usually a couple of thousand at least. And for that, there's of course transfer learning that I mentioned. There's just basically taking the ImageNet weights and then fine-tuning on your task gives you already decent result. There's data augmentation. This is one of the practical assignments in computer vision course, where you just, the last one I think, where you need just to create like multiple augmentations of an image by like some Dodge Vision or TensorFlow libraries. And what augmentations are just a simple synthetic modifications of an image, like flips, horizontal flips, vertical flips, like saturation, color, intensity, crops, rotations, zooms, crop outs. There are many of those. They usually help the model train either for robustness. This is a separate task, like for AI security, in terms of like differentiating like malware images. And but most times than not, it actually is used just to enrich your training data set. So when you have 500 images, you pretty much can apply like 2 sets of augmentations to each of the image and get like another 1,000 of images. So now you have 1,500. That's much better. That's 3 times more than, for example, 500 your initial set. So this is a way to deal with it. Of course, there are such things as like domain adaptation, future learning, even soft labels. So for example, when we don't have like labeled data set, we can use soft labels or pseudo labels for that. We can use domain adaptation to models that have specific like all architecture and algorithm modifications to particular tasks. But yeah, mostly you just use transfer learning and data augmentation. Another big deal with CNNs is that it's actually very expensive to infer during test. And yeah, for that, you basically need all the optimization you can get. It can be either knowledge distillation, it can be quantization, it can be pruning. So knowledge distillation is just a very interesting concept that distills the model, makes it a bit less in size, but usually preserves information from the weights inside. It wrangles the concept of temperature, which is just how well do certain weights respond to models output, for example. And they usually they signify, or they outline these weights should be more prioritized, something similar to tension maybe in the way, but not quite. And usually the most kind of sophisticated technique, there's of course pruning, which is very simple, usually just reduces the weight, does not reduce the speed, does not increase the speed of the model. But yeah, it's not hard to be done. It just basically prunes the network parameters, the network like neurons that are not usable in terms of like information gain. And there's of course one thing that is very important, but it's not mentioned here. It's called quantization. Usually has to do with GPUs, not with CPU. And quantization is just it just revolves around quantizing the weights from one format to another. For example, from float 32 to float 16, or from float 32 to int 16, or to int 8. Int 8 is considered one of the hardest, one of the kind of most dangerous quantizations, because usually when you quantize the model, usually you just kind of reduce the weight by reducing the allocation of memory in every single node, in every single neuron. But by doing so, you may cause the model to lose some information. This has to be, you have to be very careful. Usually with quantization, it is best to apply it to not the whole architecture, not the whole model, but rather for only the middle part, only the hidden layers. And if you quantize hidden layers, you usually don't lose too much information, but you might gain a lot of optimization momentum. But on the other hand, if you try and quantize the input layer or the output layer, things may go very ugly very soon and very quickly. So yeah, and that's also kind of an important part for production, I guess, mostly, or for some certain devices. For embedded devices, I think optimizing CNNs is very, very vital. There's a vulnerability to rotation, of course, just combated by data augmentation and regularization in general. There's decision boundary complexity. So, for example, just because the model has been able to produce a very complex decision boundary, the simple adversarial attack, like I don't know, PGD or UPGD or FGSM, even like fast gradient sign attack or projected gradient descent. I mean, basically, they can just crash the network. They can make it output something entirely different from what is actually in the image. Instead of like a horse, they could say it's a White House or something. So these in very like complex AI secure scenarios, this has to be taken into account very much. But yeah, usually it is usually dealt with via adversarially robust trainings with many different options to go there. And there's also the components positioning, like there's no kind of spatial understanding what's going on in the image. But this is where like such one of the architecture, usually there are much more options now, but back then when this presentation was made, the capsule neural network was one of the good ways to deal with it. So yeah, now it also can be done with multiple variants of pyramidal complex both CNNs models and like VATs. Usually VATs deal with this very well because they have like long-term and short-term like dependency via the attention mechanism that they employ. So yeah, there are a lot of ways to do that as well. So yeah, enough of that. Enough downsides and upsides of CNNs. Yeah, the application, the very simple part of the lecture right now. So we have the image classification is a very standard task. This could be anything. This can be like in any setting even. This could be a 2D gray. This could be 2D RGB. These could be 2D 4 channels, namely 2D RGB-A with alpha. But usually that's not the best idea to do that, like the fourth channel. Different domains, different objects, they can be of different scale, can be of different variation, intra-class, extra-class. But yeah, all these modern CNNs, they deal with this task quite well. Object detection, yeah. There, of course, traditional like segregation in one stage and two stage detectors. So one stage being like YOLO V5, YOLO V8, YOLO V7, V6, whatever. Like RetinaNet or SSD. For two-stage detectors, we have RCNN, faster CNN, masker CNN. Basically, everything that I have just mentioned is just within there. The backbone is a CNN. So there's nothing going to work without a CNN. We know there are obviously like bounding boxes, regression, IOU, Jacquard, but this feature extraction happens only with CNN. Yeah, the example of one-stage detector, YOLO architecture family. Maybe we get a good image here. So there's an input image. Then there's some weird convolutional part, which is called darknet. You can Google the architecture if you want. I'm not going to go in details here. Darknet preprocesses, extracts features. Then we have like fully connected part where we just flatten everything, and then just the anchors, region proposals, and in the end we have like four coordinates, not four floats. There's x, y, the center of the bounding box. There's width and height, w and h. Basically, just to calculate the whole box. And the object score is just how confident the model is with this prediction. Of course, there's a class probability as well. So that's just very simple look at first YOLOs here. Yeah, segmentation, of course. Just yesterday I mentioned how Stable Diffusion is built upon UNets, which are like state-of-the-art back in the day. Segmentation models, for instance, for semantic segmentation. So usually just the compression, decompression, encoder, decoder part were very similar, but also within there lies a CNN element, of course, for feature extraction. There's an RGB image as an input, the downsampling part, and then mapping and downsampling, upsampling part. In the end, just get regions on the image, kind of like on the segmentation map. So yeah, you're familiar with that as well. Yeah, now we come to kind of the bread and butter of my today's lecture for you. The tips and tricks on how to train them. Usually, like I'm going to be adding a lot of information from my personal experience. So how to actually correctly train them if you're doing this on a serious scale, not for some like pet project, but like with industry or research like lab scope. First, we start off with the regularization, what it is, what methods they are, and examples, use cases. So regularization is just the set of strategies effectively that aims to prevent overfitting, that just improves the model ability to generalize, and yeah, some potential like ways to regularize are either to increase the constraint in the model, for example, penalize like mistakes, penalize overconfidence, structure, weights, outputs, anything, add constraints like L1 regularization. If you remember, for the first couple of weeks, we talked about L1 and L2. So ridge and lasso regs. So this involves this is a type of regularization, which is basically an additional constraint regularization. Also, there's the second type is usually overfitting happens when we have too little data, too few training samples, and by artificially increasing the training set size, we may as well combat in practice combat overfitting. So not only punishing the model for like certain bad behavior during training, but also increasing the training set size are both valid strategies to make the model more robust, to prevent that terrible situation that happens when you have like when you have a loss curve or accuracy curve rather. But let's just say loss curve. I want to show something to you like that. Yeah, let's see. Here, this is not bad. Well, this is pretty bad. But I was looking for something different. Oh, such weird examples, actually. Okay, maybe this looks good. So if you have a look at this image, I'm going to do that. So if you have a look at this image, particular here, there's something weird going on. The train, which is a blue line, this is loss. In the left-hand side, there's loss, just loss. So the less, the better. The orange is validation, like typical color-validation. The train just goes down gradually, like the way it should, and like ends up in loss near zero, like 0.05 or something. Whereas validation, which is basically what we test on, which model never sees, never trains on, I mean, and never sees it kind of in a training set, then there's this sudden kind of the way it started first, like even before train, in terms of loss, and then flattened out all the way like to 20 epochs. Because we in the x-axis we have number of epochs, I suppose, like 10 epochs, 20. So in 20 epochs, the loss started to go up, which is very bad, which is where overfitting happened. The model has too much bias, has too much variance, it actually overfits, and doesn't generalize well at all on the unseen data, and is never capable of providing good results. So, and on the accuracy scale, you can see that there is just the train is almost like 100% accuracy, maybe like 90 something, but validation accuracy is like 60% even something. So that's terrible. There's a gap of, if there's a big gap between validation and train on like in terms of performance, this most likely is overfitting. I've seen like this particular figure when I was training my network for like Canada, for Toronto lab, for exoskeleton. So this is not necessarily bad, but this is very weird, and this shows for unstable data. But it's not necessarily very big overfitting problem, maybe something different. But yeah, for cases like these, for example, when the validation just spikes up, it just does not go down along the train, this is bad. The good example, I think, a very good fit is something like this, where we have loss function, we have validation. I don't know why it's flipped here, but imagine we had like train like as blue and validation as orange. So train would have been here with a smaller loss, and then validation would be high, and then would eventually gradually descend here and like end up in a very like more or less similar point along like the loss count. So going back to the lecture, this is basically all these techniques I think I'm going to show you now are just very efficient ways to combat with overfitting via regularization. So yeah, we have one first concept that I want to show you. Pretty much you are partially familiar with this. It's parameter norm penalties. So PNP sounds very weird, like the 2D to 3D transformation, fine point something, but yeah, that's a very different thing. Is out of scope here. So many regularization are indeed like limiting capacity of the models, limiting their possibility to like so to say like degrees of freedom if we're talking on like a linear models way. And we have like the subjective function, very typical J, of the inputs x, y, and parameters theta. And then in the end, there's just this sort of gradient descent that's going, it's helping the model like converge to an optimum. And we've seen before, yeah, L2, which is like ridge regression in terms of machine learning. But in terms of deep learning, L2 is also known as weight decay. So weight decay is very important concept. There are many variations of it. So there's a vanilla weight decay, there's decoupled weight decay. They are usually, not always, but usually they are encrusted within, like basically integrated in the optimizers. So for example, there's such thing as AtomW, which is a very standard atom, but not quite standard. It just uses weight decay, the L2 regularization. So there's an implementation, blah, blah, blah. So it does a very standard procedure of atom, but it also applies weight decay in itself. There's a paper, the coupled weight decay regularization. You can read through it. There's implementation in GitHub as well. You can take a look. Yeah, they describe this in depth. I'm not going to go right now too much into it, but they outline many cases where it's useful, where it's not so useful, where it's actually harmful to apply regularization here in terms of like weight decay. But besides that, you can also look up like weight decay here, which is like on paper.code. And yeah, basically, this is a technique that usually is applied to like the weights of the neural network. And the loss function is minimized for like primary loss, which is L original of W, right? And there's also a penalty norm. Basically L2 penalty, the absolute, not the absolute, the squared penalty on the weights. This looks like this particular term is weights transpose times weights. And there's parameter lambda, which is like strength of the penalty. Like the higher, the more penalization. So basically what it does is it does not let the weights grow too much. So there's even a good example here. like to the right here. There's underfitting in the left with x zeros along along the axis. There's too high of a value for lambda. So for example, there's no fit at all here. There's just a straight line, too much drag. There's an appropriate, like a perfect golden middle value of lambda for this case, where we just use weight decay and we fit the points perfectly well, which they most likely resemble like parabola or something. There's an overfitting example as well. This is what you've seen also like in random forests and SVMs. So if lambda is too small or it's never applied, the model is actually too free to move, and it actually chooses a very high degree polynomial. I don't know what this is, like 20 or something, for example. And it just does this very weird approximation where it goes down, then up, then down again, just to fit every single point perfectly. So this is basically what L2 looks like in neural networks in a form of weight decay, and this is usually used like in very complex scenarios, and it was a very standard technique. Although I gotta be honest, weight decay is not as great. Was not as great for my particular application for the Toronto paper, for the SSL paper that I did, because it just hindered the whole performance too much. I was not overfitting, so there was no need to use it too much. And actually, rejecting weight decay improved the whole model like significantly, and the final model was without weight decay. And yeah, so remember, there's of course L1 as well. L2 is kind of more important. This is a very standard norm penalty. There's also L1, which is also known as lasso. And in neural networks like L1, usually I don't know if it's too frequently used in deep learning, but like in traditional ML, this yeah, it can be used in neural nets as well. Like if you want to nullify some of the weights, but L1 is usually more about sparsity, so dropping unneeded information, unneeded predictors, unneeded feature vectors, unneeded neurons, for example, in the case of NN. So L1 basically has a built-in feature selection mechanism. What I mean by that is just it completely nullifies everything that is low probability of a good correlation of target. And yeah, basically it has been experimented with in deep learning, but I don't think it yielded many good results. So people mostly use L2 now, like yeah, exclusively use L2. Okay. Okay, now dropout. This is a very important piece, not hard. This is an easy piece, but rather important to know it. So dropout is a type of regularization when you during training. This is important, not during test time, like not during inference, but during training, you partially remove or like prune the network for one pass with certain probability. What I mean by remove part of the network, just pretend that some of the neurons do not exist, some of the connections do not exist. So basically make the model simpler for one step, like for one epoch or something, or for basically effectively for the whole training, but nonetheless, they're always different. These neurons, because there's probability on each pass, so to say. So dropout consistently improves the situations where the model is overfitting. So yeah, this is a very weird definition. But yeah, okay, we can go with that as well. This is perhaps more correct, more precise. My explanation was a bit like smooth and easy to grasp. So there's perhaps probability of, let's say, p is equals to 0.5. So we have probability 50%. So with this probability on training during every single epoch, we have a probability of each neuron temporarily dying with 50%. So basically, sometimes a big chunk of the network can die, sometimes hardly anything, like if you do it 50-50. So if more than usually things start to die out, this is not good. But 0.5 is usually considered to be the maximum value, like the maximum acceptable value on average. There could be more, but not a good practice usually. But the common values for this probability is like 10%, 20%. And basically what it does is creates like these subnetworks, like, and then ensembles them. So basically there's non-unit, non-output units inside the base network, and as long as they can be dropped without like hindering the whole architecture, they will be dropped. They will be affected by dropout rule. So the one thing from here, the key takeaway is that this decreases, this makes the model more robust. This makes the model more consistent and like generalizes better, makes the generalize better. But the thing is, the other key takeaway is you never can use this during testing, because if you ever use this during testing, like you like forget to disable dropout and you run inference, this is going to show terrible results. This is a very frequent question that is asked during like technical interviews. What is dropout? Blah blah blah. Can you use it during testing or during training, or when do you use it? So this is where you actually have to answer. This is only used during training time, not during testing. Yeah, so there's also a paper. I never looked at it, I'll be honest, because this is a rather old one. But yeah, so this is what they show. There is a standard neural net. There's a dropout applying, right? It just prunes 1, 2, 3, 4, 5, 6, 7 neurons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 survive. So obviously, okay, 8. Let's not count the output. Basically, if some neuron dies, it just does not have anything going inside it, right? These like paths, connections, and nothing going outside of it. So the model gets like the architecture gets very simplified on a certain step. And yeah, they like do a lot of testing, ablation studies, hypothesis confirmation of like standard and dropout variants. So yeah, you can read through that if you want. I don't think there's anything particularly interesting here for me. But yeah, they even show you the effect on features, how different features are when when you use dropout, for example, with probability 0.5, and when you do not use it. So, and this is the data set with MNIST, the MNIST, the one with the famous one with pictures of images, handwritten digits. So basically, what do you think is more appropriate in terms of like, even for a human being, right, for our eyes, what set of features makes it easier to understand what kind of image is written? This one or this one? Obviously, it's something on the left is not like quite right for even for our eyes. For model, maybe it's easier at some point, but this is going to converge much slower. That's going to overfit because there's a lot of noise. And in the right, we have more sparse, more clean images. Basically, not image features. And they usually help. Like, we can even see some shapes here. Like, this is 0, 1, blah, blah, blah. Like, they pretty much distinctively show us, like, give us the clue what the number can be. So this is the importance of dropout. Okay, enough of that. Let's move on. Yeah, if only. Yeah, this is what I said. Obviously, only during training. Yeah, this is a very important concept, uncertainty measurement, but a very specific use case is needed for that. This is very non-standard, so please refrain from using it during inference. Data augmentation, yeah, generating new samples. Something I mentioned before, flipping, rotating, zooming in, zooming out, changing colors, changing crops, adding some extra noise, Gaussian, non-Gaussian, whatever. Contrast, saturation, yeah, all these things mentioned, color channel shift as well. So this just artificially enriches your training data set and makes the model more robust as well. Yeah, the noise insertion is a separate topic. One of the types of data augmentation. Yeah, it can be either to the weights. So basically, trying to work with decision boundary, trying to work like with some certain regions in the optimum that push the model to make certain decision for one class. So to wait or to the targets themselves. Label smoothing, there's such a technique which regularizes a model based on a softmax. So there's like a certain number of output values, like k, which replaces them with like hard labels, like 0, 1. Basically it replaces them with a different values like epsilon over k minus 1 and 1 minus epsilon. What is epsilon? Epsilon is just a Gaussian noise scalar, usually, and makes things more robust, more regularized. So multitask learning, another part. So pretty much delegate, divide, and conquer kind of strategy. Sharing part of model across different tasks is the way to go for specific applications. So model can have two parameters, like task-specific parameters. They usually benefit from their particular task they're oriented upon, and they have like usually good generalization of that. There's of course also generic parameters, which are like not exclusive to one task. They're like pulled from different tasks and shared across them. And the idea here is the following, that the factors that explain different variations that are observed in the data, they're associated with different tasks. And some are usually shared across 2 or more tasks, and there's like this big family of cross-sharing, usually a very atypical task. I don't have much experience and even much theoretical knowledge about it. I've heard about it before, but right now I can't imagine a very good like use case for even in like industry domain. Perhaps one has to think and one has to be good at this particular type of like regularization, supposedly like multitask learning, and different type of learning, I guess, if we're talking about ML. But one last thing, I think last one, almost last one, early stopping. So early stopping is a very important concept. It's encrusted in all the libraries and all the tutorials for PyTorch and TensorFlow. There is such a class as in each of those frameworks. There's a class like scheduler, like a scheduler class, which takes an optimizer, takes learning rate, takes everything, wraps everything together, and has like a stopping rule or stopping strategy. So there's a stopping point is usually a point where you reach the best accuracy or like the best model consistency and like the lowest loss for both like validation and train, and you don't need to train more. That's why you kind of don't want to waste resources, waste time. So you stop earlier and you get the best model. How to do that? Usually, of course, for that the schedulers are employed. The scheduler basically like checks some certain heuristics, like how much improvement there is from the previous epoch, blah blah blah. If there's no much improvement within like 10 epochs, I'm just gonna stop, or like stop after epoch 50. That's also fine. If there's no improvement, there's like some certain heuristics there. So getting an early stopping and the correct scheduler is very important as well. And for this matter, I think you can read up on many early stopping techniques. You can paper with code really quickly. So this method, of course. Basically, this looks sorry. Compared to this figure, this one shows things much better. So there's just an early stopping when there's like an optimum in the validation error, right? And the training set goes down, of course, but validation goes up after this point. You need to stop early. So when the parameter updates no longer yield improvement, or after a certain number of iterations, we stop training. As simple as that. yeah, so it is effectively a regularizer. It helps like the optimization procedure and basically reduces the parameter space that we explore to a smaller volume, which is also very important. And you can also work see like similar things here, like something more new, like where this is used, but this is not particular in the task. Normalization activation layers. Okay, yeah, whatever. So yeah, that's early stopping, kind of an important part. But usually, in my experience, I have not been bothering with this too much. I just used a very standard scheduler, and that's it. And that was good. So parameter sharing. So parameter sharing is something that just was mentioned for CNN, so that the kernels are shared and they are all used over the image. And in the recurrent neural network, the parameter sharing happens when we have like sequence-to-sequence part, partially when we just pass information from one step to another. So parameter sharing may actually allow the model to reduced complexity, less variance, better fit, blah, blah, blah. Very good. Nice thing for certain architectures, and actually overall nice thing. I think this last part, last slide, the kind of I'm going to talk explicitly on adversarial training. Yep, this is what I've been doing in my master's. During my master's, my thesis was like studying adversarial. I don't remember my thesis. God bloody hell! Like adversarial attacks and defenses, of course, but specifically there was a metric called adversarial accuracy. So just to make a setting, to set the setting, there is a task of adding a very small portion of noise to an image so that the model or like the system does not notice it. And then this kind of noise very specifically perturbs the image so that for the human eye, it is indistinguishable from the same original image. But for the model, it just produces a very completely broken label, like spaceship for a car, right? And basically there's an example here, like different labels, different confidences, blah, blah, blah. There's this one piece of noise, like 0.007. There's just a very small epsilon, like 8 divided by 255, for like 0.03, which is like equivalent of that. But this is what I've been experimenting with. So adversarial accuracy is just an accuracy of the model. Which is only like different with the part that it's being fed adversarially perturbed images. So the like malicious images with like noise, certain noise, and how many of those images does the model actually predict correctly. So if the original accuracy or natural accuracy of the model can be like 90% in classification, right? Like for many classes. Then if it's not trained correctly with adversarial training, then this model may achieve as much as like 2% robust accuracy. 2%, that's very little. 2% of robust accuracy if the images were to actually be perturbed or like messed around with somehow. So the task of like adversarial learning, training, and defense and attacks is just to mitigate the effect of attacks, make the model more resilient, more robust, more R-separable. So in my master's, I was doing a research on an alternative metric, which is called adversarial sparsity, which is not only like the actual hard label classification, whether the model predicted the correct sample or not, but also for how many potential perturbation being like this combination of malicious pixel inserts and swaps and stuff like that, how many are there for a certain image? If there are a lot of them, it's very likely that the attack is going to find one of them. If there are very few of them, like this, like radius, this epsilon or just r, is going to be like limited. If there are very few instances, then it's very unlikely that the model is actually not the model, but the attack is actually going to find this perturbation, insert it quickly, and all that stuff. So this is a very separate task and rather cool application. Back in the day, I used to think it was a good idea to like delve deep into this. And believe me, this is a very active area of research. but not really now. I think my opinion has changed as I basically I want to go something more hands-on oriented, like robotics. Adversarial is more theoretical, and by any means, I think this is very viable and is both research and kind of and both research and maybe industry, even perhaps somewhere in certain specific places, in certain companies. So yeah, that's that. A couple of words on how to visualize CNNs. Yes, there's GradCam. GradCam, it's just a method, and you can look it up in Python libraries. GradCam is just a gradient-based method. It visualizes the parts of the image. Well, basically, given certain output, the real or possible. So there's an original image, there's GradCam dog and GradCam cat. There's visualization event. So where it is, as we know, this is a very old model. As we know, now we have like image captioning classification models that just take the image and they show you, like they say there's a cat in certain coordinates with a mask or with bounding box, with whatever, and do many more advanced things. But back in the day, GradCam was the way to go. Yeah, we're not going to go into the main idea here, honestly. Maybe I'm going to look this only for myself. Estimation, even informs gradient value. Yeah, okay. There's some backpropagation, global average pooling. Global average pooling sounds like pooling layer, but slightly intrinsically different. And in the end, we have just a ReLU with linear combination of those. Okay. Yeah, we're not going too deep into this. And yeah, that's pretty much it. There's 10 minutes left. I think that's enough for today's review lecture. Yeah, please do read if you want, if you have like more wish to on certain papers. There's of course the deep learning book, but found colleagues Joshua Bender. There's also like ArcSIF papers that I recommend, which are how CNNs see like the world. There's a survey, very many different architectures there, many like conclusions, and yeah, that's pretty much it. Дякую за увагу. Thank you for your attention.
Дякую. Дякую.
У нас лише Катерина. У вас є питання?
Ну, я скажу так, мені важко інколи сприймати це українською мовою, тому англійською було ще важче сприймати, тому питань поки мені важко якісь формулювати, я буду ще переглядати запис, ну, щоб включитися в тему.
Окей, добре.
Дякую вам.
Дякую, що прийшли. Практично, я думаю, буде коротеньке, там ще домашки якісь, тому да, приходьте. Зустрінемось.
Добре, дякую.
Ой, за 40 хвилин.
За 40. До побачення. Не прощаємось, дякую.